reacting with H2O to form H3O positive plus an HSO4 minus. So, I mean, this is what happens when you put sulfuric acid in water. The sulfuric acid donates an H plus to the water to form H3O positive, or the hydronium ion. Same thing with hydrochloric acid. Any of the acids you put in water, this is actually what happens. Now, if we combine this with the equation above, we end up with another version of this another version of the overall equation. I think they both appear on the mark schemes if you look. And I just want to cover it because some people will try and learn different versions when they've looked at the mark schemes, and so they're both fine. I'm just explaining why. So if we combine these together, we get 2H2SO4 plus the H2Os are going to cancel. Goes to H3O positive plus NO2 positive plus 2HSO4 minus. So that is another valid way of writing the reaction to form our reactive intermediate. So we'll call this one A. That's fine. That'll be on the mark scheme. And B, that will also be on the mark scheme. What's important though is what I think is called the nitronium ion. That's the thing that's actually going to go and react with benzene. So this is I think it's only 1 mark, because you can in principle just memorize it. So you're going to start by writing out this as an overall equation for the production of the reactive intermediate. So now looking at what then takes place between the nitronium ion and benzene. So the nitronium ion is as such. You don't have to represent it like this. You can also represent it just as N2O. Make sure the positive's on the nitrogen though. Now we can then have our benzene, and we're going to donate electrons from the delocalized ring. So not from one of the bonds, from the delocalized ring of electrons towards the nitrogen. If you've done it like this, you do it to the nitrogen like so. Now that forms a bond between one of the carbons and the nitrogen. Now if let's say you went above A level, if any of you study chemistry at university, you're going to have to be a bit careful about how you draw this arrow with a little bit more precision. But for the moment, for the time being, you can actually choose whichever carbon you like that the nitrogen bonds onto. It doesn't really matter what you did for your arrow, as long as it comes from the ring. You can attach the nitrogen onto whichever carbon you want. What you'll often need to look at is where is it on the product that you've been asked to make, and so you just make sure you attach it in the right place. So I'm going to attach it here. I'm not going to draw any extra structure. I'm always just going to put NO2. Don't try and draw any extra detail because you'll get it wrong. The Lewis structure, the one with the bonds and everything, for the NO2 group is really weird. So don't try and draw it because you'll just get it wrong. So just ignore that. Now the hydrogen that was attached, there's one on each of the carbons. That hydrogen's still there, so I'm going to draw it. I'm going to draw it because I'm going to need to use it later. Then we need to draw the remainder of the aromatic ring. Now to draw the remainder of the aromatic ring, you're going to draw basically a horseshoe shape from the carbons either side of where you attached the NO2 group. Now your horseshoe, so it needs to extend from the carbon either side of where you attached your electrophile, must not extend past the position of the carbon. So you see that dotted line I just drew, your horseshoe mustn't extend past, and the same on this side here, mustn't extend past. The final thing is we've got this positive charge, we've got an excess of, we've got a lack of electrons, the ring donated away electrons, it's lost electrons, we've got to have a positive charge, and you draw it in there. So this is the halfway point. Now this aromatic ring is incredibly stable and it really wants to reform. We want to get some extra electrons back into the ring and reform the full aromatic ring, as it's incredibly low in energy. And the way we do that is by breaking this CH bond. So we take the electrons out of the CH bond, and we show them going back into the ring. That reforms the aromatic ring. And produces an H plus ion. And there we have our completed electrophilic addition reaction or mechanism for the nitration of a benzene molecule. Now, something that does very occasionally show up is further nitration. So this molecule, this is called nitrobenzene. This can go on to react further. So if we've got some more NO2 positive, I just realised I put N2O, that is incorrect, it's NO2. Sorry about that. If you've got some more NO2 positive, these two can react with each other, and we go through those series of steps again, and we can end up with this. And actually, it can react again, and we can nitrate it 3 times. Now, each of these nitrations gets more and more difficult to do, though, as this NO2 group, you've got 3 highly electronegative atoms. They're pulling electron density out of the ring. So there's a lot of electrons packed into one space. This is why it's able to act as a nucleophile and donate electrons away. But this NO2 group is electron withdrawing. It's pulling electron density off of the benzene ring, and so this is a little bit similar to when we looked at the amines. With amines, we were considering those CH3 groups dumping extra electron density onto the nitrogen, making the lone pair more available. This NO2 group, rather than donating electrons, it's withdrawing. It's taking them away from the ring. So each time you add a nitro group on, so this one with 2 nitros instead of 1 nitro, this ring is a worse nucleophile. The electrons are less available to be donated away. So the reaction gets more and more difficult to do each time. So this first stage to form nitrobenzene, that will take place at temperatures above sort of minus 10 degrees. To get dinitro, you need to get above a temperature of like 10, 15 degrees, and then to get to trinitro, it needs to go above something like 50 degrees. The problem with this, though, is that the reaction is exothermic. It gives out a load of heat, and so if you're not careful, when you're trying to produce nitrobenzene, it's going to heat up loads, and you're going to end up rising above the minimum temperature, above, like, say 10 degrees, and start to form dinitro. And if it really starts to get out of control, it might trinitrate. Now, the reason this is potentially very, very dangerous, aside from not producing the chemical you want, is, I'll give you a little hint. There is, if we take benzene and add this CH3 onto it, that would be called methylbenzene. The old name for it, though, is toluene. It's sometimes used as a solvent. So if you look on things like, it's used as a solvent in paint. So if you've got a pack of paint that your parents had for doing some DIY, if you look on the back, it might say toluene as the solvent. It's just the old name for methylbenzene. Now, if we were to nitrate this 3 times, I mean, the new name would be trinitromethylbenzene, or it might be methyl trinitro. Anyway, the old name for it, though, is trinitrotoluene. If we were maybe to come up with the acronym for that, so trinitro-toluene, and it forms TNT, which is possibly the most famous explosive. So the problem with nitration is that you end up forming explosives. So these molecules have a tendency to detonate. So you have to be incredibly careful when doing it. So at university, I did the nitration of some sort of benzene derivative, It wasn't just benzene. It was probably toluene. Did the nitration, and I had to do it in an ice bath and very, very carefully watch the temperature, and only very slowly add the acids in there to start nitrating the I think the toluene, just to make sure it didn't get above. I think it kept it below 5 degrees at all points. It took a long time to add all the reagents together, and I've heard of I think in labs producing medicines, because actually nitrobenzenes, so these benzene rings with nitro groups on, there's actually quite a few medicines that have that structure within them, and so they're trying to manufacture these medicines, and things got too hot and they made a load of explosives, which obviously did not end well. Right, now the second reaction of that falls under the mechanism of electrophilic substitution is the Friedel-Crafts acylation.